Okay, in this video we're going to learn the definition of a secant line. We're going to learn how to calculate the slope or slopes of a curve, and we'll learn the definition of a tangent line. So slope is the name of the game in this video. This concept of change in y divided by change in x, delta y over delta x. You've seen it presented many times throughout your years of mathematics. Perhaps the first time you saw it was in 8th grade, and mainly in a geometric interpretation where we said that the slope, and we give the slope usually the word or the letter m to stand for it, is defined to be the rise divided by the run. In 10th grade we probably calculated slope with this formula right here, y2 minus y1 divided by x2 minus x1. And then at least if you had me in pre-cal, we calculated slope in a different manner with different notation and with different interpretations, using the expression f of b minus f of a over b minus a. So what's the big deal, right? Well, for a line, for linear function, this number m is a constant. It's always the same, regardless of what 2 points you use to calculate this. So we don't usually talk about this concept with anything but a line because it comes out to be different. Okay, but let's just go ahead and talk about that. Here I have the same curve drawn 3 times, the same function, and I have locked in point A in the same location, but point B has moved. Picture 1, it's up here at 4, 4.7-ish. Here it's at 3.2, 3.1, and here it's at 3.1, 1. Okay, so point B has moved around, and you can clearly see that these 3 lines have different slopes. Okay, so when you talk about slope connecting 2 points, or a line that connects 2 points on a curve, you're not going to get the same answer every time. So let's start with the definition here. Okay, a line that connects 2 points on a function's graph is called a secant line. And I'll apologize right now because I know in mathematics we reuse words a lot, and they're gonna mean different things in the different contexts. So you've seen secant used in terms of circles, and you've seen secant used in the world of trig, but now secant's going to have a new meaning in this context. Okay, and there's some connection because when you drew a circle and drew a line through the circle in 2 spots, you called it a secant to a circle. And this is kind of the same idea here, where this line goes through the curve in at least 2 spots. Okay, and then there's an interpretation that goes along with this. The slope of a secant line on the interval AB is interpreted as the average rate of change of your function f on the interval AB. Okay, so when you talk about a line, this number is always the same. It's not only the average rate of change, but it's the actual rate of change for a line, how fast the y value changes with respect to the x value. With a curve, since these numbers always come out to be different just about, we say it's the average rate of change. It talks about what happens on average between A and B. How much does the y change with respect to the x? Okay, so we're going to go ahead and explore this a little bit using GeoGebra, and that's going to get us to what we want to talk about today as far as how do curves have slope that has any meaning to us. So here's a picture of a curve in red, and I have point A at x equals 1, and this point is locked. It's not going to move. But point B is going to move, and I'm going to move this point B closer to point A. All right, and as I do that, notice that the slope of this line changes. Okay, so here we have a positive slope, maybe not quite equal to 1, but positive. And as I move the point B closer to A, the slope's changing. It's getting smaller. Here now it's almost to be 0. Now we have a negative slope, and I can continue to make B get closer to A. And what starts to happen is that this blue line, this secant line, starts to hug the red curve better and better the closer B goes to A. Okay? And you might say, hey, A and B are pretty close together. But I'm going to go ahead and I'm going to zoom in using the pinch feature on the computer. And A and B get farther and farther apart, and you can see that there's still some gap between the blue secant line and the red curve. So we can go ahead and continue this and move B closer and closer to A. And we can do some more zooming. There's still a little bit of a difference between the blue secant line and the red curve. And I'll do a little bit more here. And one more time we'll zoom. And at this point, it's almost impossible to see the difference between the red curve and the blue secant line. In fact, the red curve has now appeared to be the same as a line. Okay, we call that local linearity. Curves, when you zoom in, smooth curves, when you zoom in, look like lines. And if they look like lines, then they have slope, okay, to a certain extent. All right, let's head back to our notebook and talk about this some more here. Okay, by making our 2 points on a curve closer and closer together, the secant line that connects the 2 points and the actual curve become indistinguishable, hard to tell apart, right? So what does that mean? Okay, it means that curves don't have slope between 2 points. Okay, that's the same. They're always different. Curves will have a slope at a single point. So we can talk about what is the slope of the curve at x equals 1. What is the slope of the curve at x equals 4? Okay, specific locations. Whereas before you had to talk about, okay, what's the slope between these 2 points? And you'd always get a different answer. Okay, we'll get a single answer, but only at a single point. All right, let's talk about now how that's going to happen. So this is a picture of just a general curve. Nothing special about it. It's going to be called f in this photo here. And this point here is the locked point. Okay, so I'm going to call that a comma f of a. A is a number. In this case, it's 1. You can see that, but it could be anywhere on this curve. It doesn't have to be a 1. This is a general discussion right now. Okay, a comma f of a. And then this is the point that's going to move. Okay, this is the movable point. So its x-coordinate is variable. It can change. Okay, so it makes sense to label this point up here as x comma f of x. Okay, now I've drawn a secant line in here. The slope of this secant line is f of x minus f of a. That's the change in the y values, divided by x minus a. Now, what I want to do is I want to make these 2 dots, these 2 points on the curve, get closer and closer together. Okay, by doing that, I make the curve look like a line, and the line and the curve become just about the same thing. Okay, so how do we do that? Well, we need to make the x value of this dot get very, very close to a. In other words, we need x to approach a, and the mechanics we have to do that in calculus now is the limit. Okay, so this is the process right here to create and find the slope of a curve at a special point. Okay, so let's write a definition here. All right, the slope of a curve, and we'll call our curve f of x for argument's sake. Okay, now you have to say at a specific location. So at x equals a, okay, is found with this calculation, and we give this calculation a symbol. Okay, so let me put here the slope of a curve f of x at equals a denoted, okay, as f with a little exclamation, not exclamation point, little quotation mark here, okay, and I put an a in parentheses here. Okay, this is red, f prime of a. So this is the symbol for what this is finding. So this is the slope of f at a, and this is equal to, this is found by doing this calculation up here that we just derived. The limit as x approaches a, f of x minus f of a over x minus a. So f prime of a stands for the slope of the curve, f at a. Just as the slope of a secant line had an interpretation, the slope of this curve is going to have an interpretation as well. So I'm going to go ahead and type this one and say that this slope at x equals a is interpreted. So when we start talking about functions having some real world meaning, okay, this is where this is going to come into effect here, is interpreted as the instantaneous rate of change of f at x equals a. So in other words, how fast is your function changing right now, right at this moment? Okay, not on average. Do an example calculation. All right, we are interested, we're asked to find, okay, what is f primed of 1 for this curve here? 1/2 x cubed minus 2x squared plus x plus 2. Okay? At the point 1, 3/2. So what is the slope of the curve? Well, the definition says we need to take the slope of the line that connects the 2 points, f of a to f of x. In this case, a is 1. Okay, so we're going to do, I'm going to write it out in long form first, and then we'll substitute in the pieces. We're going to do f of x minus f of 1 divided by x minus 1, and then we're going to take the limit as x approaches 1. Okay, that's the calculation that needs to be done. In this case, f of a is f of 1. Okay, now let's fill in the pieces here. The limit is going to carry on down until I've actually taken the limit of my function. In this case, my function is a slope function. Okay, f of x is given. It's this formula here, 1/2 x cubed minus 2x squared plus x plus 2, and I'm going to subtract f of 1, and f of 1 over here is 3/2. That's the y value when x is 1, divided by x minus 1. To make the calculations a little bit easier, I'm going to multiply top and bottom by 2, which is really not doing anything to this expression. It's just going to change what it looks like. This is the number 1 disguised. So that's going to get rid of the fractions, make this a little bit nicer for us. Our rules say when we do limits, we do a plug-in first. So we mentally plug this in. The bottom is 0, and I'm going to bet that the top's going to be 0. So we get 1 minus 4, negative 3, plus 2, that's negative 1, plus 1. So I do have 0 over 0. Indeterminate form, which means I got to get busy doing some more work. Usually that's meant factoring. So this needs to be factored, and hopefully it's going to be factored with x minus 1 as one of its factors. Okay, and I could try factoring by grouping, okay, because there's more than 3 terms. It's not a trinomial and it's not a special pattern. But if I want to do this quickly and not worry about the factoring, I'm going to do synthetic division on x cubed minus 4x squared plus 2x plus 1 divided by x minus 1, and I'll carry the 2 on down. So synthetic division says put the number that we're dividing by, x minus 1, on the shelf, and here we're going to write the coefficients of my polynomial. 1, negative 4, 2, and 1. We bring the first number down, we multiply, and we add. We multiply, and we add. We multiply, and we add. Since we got a remainder of 0, I know that this divides evenly. So my limit now becomes the limit as x approaches 1. The numerator is going to factor as x minus 1 times, here's what's left over, x squared minus 3x minus 1. So there's a little pre-cal review of synthetic division for you there. Okay, and I'm dividing by what? 2 times x minus 1. Okay, and now I'm going to go ahead and do what? I'm going to split this limit into 2 pieces so I can show you where the unnecessary 1 is located. So the piece that's going to come out is x minus 1 over x minus 1. That's going to remove the 0 over 0 problem. And I'm going to multiply that by the limit as x goes to 1 of what's left. Okay, remember that's one of our limit properties, is I can make the limit of a product into the product of 2 limits. So there we go. This limit here is 1 because x minus 1 over x minus 1 simplifies to be 1 for all numbers except 1. And now here's what I've got. Limit as x goes to 1 of something that's not too bad. I can probably do a plug-in at this point. 1 minus 3 is negative 2 minus 1 is negative 3 over 2. So I get negative 3/2 is equal to f primed of 1. What does that mean? It means the slope of this curve at x equals 1 is negative 3/2. Okay, in a second we'll take a look at a picture and verify that. But first let's come up with a definition. So a tangent line, here we go again using in multiple contexts. So we had a secant line, now we have a tangent line. Okay, a tangent line to a function f at x equals a is a line that, 2 things. Number 1, passes through f at a comma f of a. So they intersect the same spot. And 2, has the same slope as f at a of A. So a tangent line goes through a certain point on a curve and has the same slope of the curve, or same slope as the curve at that point. So let's take a look real quick. We have a slope of -3/2, and if it's going to go through this point 1 comma 3/2, let's take a look and see what the equation of that line would be. Okay, we would get y equals 3/2, that's the y value, plus the slope is -3/2 times x minus 1. So let's go to GeoGebra now. Now we're saying that the slope of this curve at x equals 1 was -3/2, and therefore the tangent line would have equation 3/2 minus 3/2 x minus 1. So what am I expecting to see when I hit enter? I'm expecting to see a line that goes through point A here and should hug the curve very tightly. Let's see. Alright, does it look pretty good? And if I start to zoom in, the more I zoom in, the more the red curve should start to look like that black line. Why? Because they have the same slope. They go through the same point, and so if I'm really super zoomed in, they should look almost identical. Alternative definition for finding the slope of a curve at a specific point. Sometimes it's easier to use this definition, so we'll present it here. So here's another curve. This is f. Nothing special about f. Let's lock in the point a comma f of a. That's a stationary point. That's not going to move. Instead of labeling the second point as x f of x, let's do a little different exercise here. Okay, we're going to say that a and b are a certain distance apart. Okay, so I'm going to go ahead and draw this dotted line here, and I'm going to call this distance h. Okay, so if this is A and I've gone h units to the right, then the x-coordinate of point B up here needs to be A plus h, which makes the y value f of A plus h. Okay, so if we're going to connect these two dots with a line, then we can calculate the slope of that line, and the slope of that line is going to be f of a plus h minus f of a, difference of the y values, divided by the difference of the x values. Well, the x values are a plus h and a, so if I subtract those, I'm just going to get h. All right, now what do I need to do to make these 2 points close together? Well, I need this distance h to shrink to be almost nothing. So in other words, I want the distance between the two dots to be approaching 0, and the mechanics that we have to do that now are to take the limit. So this is an alternative definition, another way to calculate f primed of a. In class, you're going to have practice doing it both ways, so I wanted to show you that. And let's do a quick calculation with this curve being f of x equals x squared at the point 1 comma 1. So, example, using this definition, f of a plus h, so what is that going to look like? Well, f of x is x squared, and we're looking at a is equal to 1, so we're going to plug in 1 plus h into the function x squared, and when we do that, you're going to get 1 plus h squared. Okay, minus f of a, what's a? A is 1, so f of 1 is 1, and you'll be dividing by h. We do a quick plug-in, and we notice we get 0 over 0 as we should expect. So we got to do some work here. Okay, I'm going to go ahead and expand the top, the numerator. So we're going to get x squared plus 2h plus 1 minus 1. So they cancel out. Nice. Still dividing by h, still taking a limit. And I notice that numerator and denominator both have h over h as a common factor, and I'm going to go ahead and perhaps skip a step here and already make this into 2 limits. So h over h times the limit as h approaches 0. What's left when I factor out an h from the numerator is an h plus 2 over 1. Okay, this first limit is 1. H over h simplifies to be 1. And then we do a plug-in on this second limit, and we get 0 plus 2 over 1, so 2. Okay, so Another way to calculate the slope of a curve at a specific point, using this definition, and we get that f primed of 1 is equal to 2.